Hello, welcome to a portrait of linear algebra. My name is Socrates. Our video for today is about operations on linear transformations and matrices. So if you've been following along, we started out with operations on vectors. We learned how to add and subtract and multiply a vector by a scalar. And then we also talked about the dot products a little bit later on. So from vectors, we created matrices. And now we're going to talk about operations on matrices. And since we've already talked about linear transformations, we're also going to talk about operations on linear transformations. So exactly what are these operations? So we are going to talk about addition and scalar multiplication of linear transformations and matrices. We are going to compose linear transformations, and we are going to make a general definition for matrix multiplication. Now, when you studied your algebra or pre-calculus, we learned how to add two functions. For example, if you had f of x is x squared and g of x is 2x plus 5, then f plus g is just x squared plus 2x plus 5. You just add the two formulas for your functions together. So it's exactly the same idea for linear transformations, but when we add functions together, we have to worry about domains because both functions have to be defined before you can add their outputs. So in the same way, if we have two linear transformations, T1 and T2, they must have the same domain and the same codomain. So here you have both T1 and T2 going from Rn to Rn. And of course, if K is any scalar, then we can define the sum, the difference, and the scalar product of T1 and T2 as T1 plus T2 and T1 minus T2 and K times T1 are all transformations which are also going from Rn to Rm. So the same domain, the same codomain as the two original transformations. How do you define them? Well, they are again functions, and their actions are given as for any input v from the domain Rn, T1 plus T2 of v is just T1 of v plus T2 of v. So you take the outputs of T1 and T2 when you input v, and then you just add them together. Similarly for the difference, T1 minus T2 of v is just T1 of v minus T2 of v. What is K times T1 of v? You take the output T1 of v, and then you multiply that answer by K. Now, let me be honest with you. That definition is hiding the word linear transformation, okay? So it's not obvious that T1 plus T2 and T1 minus T2 and K times T1 are all linear transformations. In other words, are they also additive? Are they also homogeneous? So we're going to prove later on that, of course, they are. And that's because we can find a matrix for them using the matrices for T1 and T2. But as a bonus, let's prove the additivity property just using the definition. So what is the meaning of T1 plus T2 evaluated at V plus W? So to prove additivity, at the bottom line, we have to show that this is the same as T1 plus T2 evaluated at V plus T1 plus T2 evaluated at W, the additive property. Okay, so how do we get there? Well, what is the definition of T1 plus T2 evaluated at V plus W? It means that we take T1 and we evaluate V plus W, and then we take T2 and then we evaluate it as V plus W. Okay? So, we do know though that T1 and T2 are both linear transformations. So they are both additive and homogeneous. All we need, of course, is the additivity property. So the first expression is the same as T1 of V plus T1 of W. Okay, we have the additivity property for T1. And similarly, we have T2 of V plus T2 of W for T2 of V plus W. T2 is also additive. Okay, so now let's use the commutativity property. Let's rearrange the furniture. So we have these four terms, and we are just going to switch. We are going to bring the terms containing V closer to each other. And of course, in so doing, the terms containing W are also closer to each other, right next to each other. Well, what have we got here? This is T1 of V plus T2 of V. But the definition works both ways. This is also the same as T1 plus T2 evaluated at V. So let me just copy this one over here, and I will just erase the plus W over there. But we also have T1 of W plus T2 of W. Same idea. That is simply T1 plus T2, this time evaluated at W. There you go. Mission accomplished. T1 plus T2 evaluated at V plus W is exactly the same as T1 plus T2 evaluated at V only, plus T1 plus T2 evaluated at W only. So T1 plus T2 is also additive. It's just as easy to show homogeneity. If you have K times V here, you should get K times V here, and K times V. I'm sorry, just one term. K on the outside of T1 plus T2. Okay, so let's do this example. So let's have T1 and T2, both of them going from R3 to R2. So here are their formulas. X, Y, and Z will go to the vector 5x plus 3y minus z in the first component, and negative 2x plus 7z in the second component. So notice there's no y term over here. There's nothing wrong with that. Where will x, y, z go under T2? It will go to 4x minus 9y, so there's no z, and x plus y minus 6z. Okay, so hopefully we're now experts at putting together a matrix for a linear transformation. So how big are the matrices? We're going from R3 to R2, so we should have 2 by 3 matrices. So yeah, 2 by 3. What's in the matrix for T1? We have 5, 3, minus 1 in row 1, minus 2, 0, 7 for row 2. Again, there is no y there. Similarly for T2, we have 4, minus 9, no z, 0z for row 1, and 1, 1, minus 6 for row 2. Okay, so quick review of how to assemble the matrix of a linear transformation. Let's find a formula for the sum of these two linear transformations. Okay, so the definition said all we have to do is take the output for each transformation, add them together, copy and paste, and copy and paste. So we're just going to add those two output vectors together. Okay, so what do we get? 5x plus 4x is 9x. 3y minus 9y, so minus 6y. And we have a z term. We have a minus z from the first, no z in the second. Second term, we have negative x plus x, negative 2x rather, plus x. So we get negative x. And then we have y by itself, so plus y. And then 7z minus 6z, so that is positive 1z. So that is the formula for T1 plus T2. Okay, so we said earlier that we're going to show that the sum is a linear transformation by creating a product, a matrix for it, so that its output can be written as a matrix product. So can we write this output as a matrix product, as usual? So just like what we did for T1 and T2 individually, we can write that as 9, minus 6, and minus 1 for the first component. And we have minus 1, plus 1, plus 1 as its second component. So of course, that is a matrix for our linear transformation. So we have succeeded in showing that T1 plus T2 is indeed a linear transformation. Okay, so we will write that the matrix of T1 plus T2 is this matrix, 9 minus 6 minus 1, minus 1, 1, 1. Let's compare that to the matrices for T1 and T2 separately. What could be the connection? Well, where did 9 come from? 5 plus 4. Where did negative 6 come from? 3 minus 9. So, of course, the entries of the matrix for T1 plus T2 are simply the sums of the pairs of corresponding entries in the matrix for T1 and the matrix for T2. So, of course, we will generalize this a little bit later. All right, so this time let's take a look at a scalar product. We have the formula for T1, we just copied it. Let's compute negative 4 times T1. What does it do to x, y, z? So the definition says, just take negative 4 and multiply it to the output for T1. Okay? That's just a scalar product. So we know how to do that. Multiply the first component by negative 4. So we get negative 20. And then multiply 3 by negative 4. So we have minus 12. Negative 4 times negative 1 is positive 4. Next, negative 4 times negative 2. So that is positive 8. And negative 4 times 7, that is negative 20. Okay, so just like for T1 plus T2, we can create a matrix for this function because that's just minus 20, minus 12, and 4. So if you multiply by x, y, z, you'll get minus 20x, minus 12y, plus 4z. In the second row, we will get 8x, no y, and minus 28z. So if you multiply that by x, y, z, you'll get exactly 8x, 0y, minus 28z. How could this possibly be related to the original matrix for T1? Minus 4 times T1. So it looks like, of course, every entry in this matrix is simply negative 4 times the corresponding entry in our original matrix. So of course, we are going to generalize these two observations in our next definition. Okay, so in our last two examples, we were talking about corresponding pairs of numbers. So to define these operations on matrices, let's bring back the notation that we saw earlier, where if you have a matrix A, you can enclose A with parentheses and put the subscripts I and J, where I is the row number and J is the column number. And the symbol means you give the entry of the matrix A, which is found in row I, column J. So we have two matrices A and B, and they must be the same size, m by n. Okay, so we saw 2 by 3, 2 by 3, and the matrix for the sum is also 2 by 3. And of course, k is any scalar. We will define the sum, difference, and scalar product of these matrices. So they're written as a plus b, a minus b, and k times a. Okay, you can put the dot, or you can just concatenate the symbols k and a, as usual. So, what is found in a plus b? The entry in row I, column j of a plus b is just the entry in row I, column j of a, plus the entry in row I, column j of b. So that is what this equation means. And similarly for a minus b, you just subtract from the entry in a the corresponding entry in b. If you want the entry in k times a, you simply get the entry in a in row I, column j, multiply it by k. And that's what you write down in the matrix product. Similarly, in particular, if you want the negative of a matrix, negative a, you can define it to be negative 1 times a. So you multiply every entry in a by negative 1. So of course, we talked about matrix addition here. What happens when you add a to negative a? You will of course get all zeros. So you will get the 0 m by n matrix. Alright, so we talked about adding just pairs of numbers found in A and found in B. But we said, you know what, we can also make matrices by assembling vectors into columns or by assembling vectors into rows. Alright, so we already talked about partitioning matrices into rows or into columns. So here's another way to think about addition and scalar multiplication of matrices. Suppose you partition A and B into their columns. Okay? A1, A2 to AN are the columns of A, and B1, B2 to Bn are the columns of B. Then, what is found in A plus B? Simple. In column 1, you will find A1 plus B1. In column 2, A2 plus B2, and so on. And of course, this is easy to see because when you take pairs of numbers, they belong to a column or to rows. So when you add them together, then you can just think of them as part of a column or part of a row. So that's this formula. And the same thing for A minus B and K times A. You simply have K times A1, K times A2, up to K times AN. Now, how about if you partition into rows? So, of course, there is a similar theorem. If you have A and B partitioned into rows, R1, R2 to Rm, and B into S1, S2 to Sm, then what will you find in A plus B? In row 1, it's just R1 plus S1. In row 2, it's just R2 plus S2, and so on. Same thing with the difference, and same thing with the scalar product. All right, so back in chapter 1, I believe, when we first introduced the concept of a matrix product, I think it was chapter 2, we said that there were two properties for the matrix product that are similar to what we have for just vector arithmetic. Okay, we have the additivity property and we have the homogeneity property. So a times x plus y is the same as ax plus ay. A times k times x is the same as k times a times x. Additivity and homogeneity. Now that we know how to add two matrices together and how to multiply a matrix by scalar, we have these two additional properties, which are also called additivity and homogeneity, but for slightly different reasons. So this time, if you do A plus B first, and of course they have to be the same size matrices, and then you multiply by V, it's the same thing as getting A times V plus B times V. Again, additivity almost the same as the distributive property. All right, but this time it's the matrices that are added together, not the vectors. Okay, and similarly, you can multiply a matrix times a scalar. So that's what we just did. And then multiply that to V. It's the same as multiplying A to V first, then multiplying by K, or multiplying K and V first, and then multiplying that by A. So let's prove the first property. Okay, so it's a little bit long, but I'm going to scroll down when the time comes. So we want to show that the quantity A plus B times V is the same as A times B plus B times V. Okay, so the idea is to partition A and B into its columns, right? So let's work on the right side. What is A times B plus B times V? Well, we know what A times V means and how to write it out. And similarly for B times V. What is the meaning of A times V? You take linear combinations. You have V1 times A1 plus V2 times A2, and so on. So that was the definition of a matrix product. Similarly, for B, we have V1 times V1 plus V2 times V2, and so on. Okay, what happens next? Well, we have a commutative property. Let's bring the terms containing V1 closer together. So let's move V1, B1 next to V1, A1. We get V1, A1 plus V1, B1. Similarly, we have plus V2, A2 plus V2, B2. Move them together. Okay, you do that for each column. And then we have the distributive property or additivity for vector addition over scalar multiplication. So the first pair can be written as the quantity A1 plus B1 times V1. And the same thing for the second pair, and so on. Okay, but now it's time to scroll down. We can think of this long product as a matrix product, okay? Where now that single vector, after you add those two together, is in the first column. This single vector, after you add them together, is in the second column, and so on. And the coefficients are here in a column matrix. So we have V1, V2 to Vn. Who is this? That's what we just said is the matrix A plus B. A plus B getting multiplied to the matrix. And that is your additivity property. All right, so now we are ready to prove that these combinations, T1 plus T2, T1 minus T2, and KT1 are actually linear transformations by creating matrices for them. Where will they come from? Of course, from the original matrices for T1 and T2. So we have T1 and T2, again, going from the same domain to the same codomain. We have matrices for them, matrix for T1 and matrix for T2, and we have a scalar K. Then, for any vector V in the domain Rn, T1 plus T2 evaluated at V is the same as multiplying the matrix for V with the sum of the matrices for T1 and T2. Similarly for the difference, and for K times T1 at V, you take V and you multiply it by the multiple of the matrix for T1 by the scalar K. By the uniqueness of the matrix for a linear transformation, this tells us that the matrix for T1 plus T2, which we write this way, has to be the matrix of T1 plus the matrix for T2. And similarly for the difference and for the scalar multiplier. Okay, so let's prove it for t1 plus t2, and of course the others, t1 minus t2, k times t1. It's the same idea. So, what is quantity t1 plus t2 evaluated at v? So we know from the definition that this means take t1 of v and add t2 of v. Okay, so let's put an equal sign there. But we know that we can compute t1 of v by a matrix product. Okay, so who is the matrix for t1? Let's call it A. So the first term is just A times b, and the second term is just b times v. But wait a minute. We just saw A times b plus b times v. We said that that's exactly the same thing as A plus b times the vector v, the additivity property. Okay. So this tells us that the matrix of t1 plus t2 has to be A plus b. And of course, who are A and B? A is the matrix of t1 and B is the matrix of t2. So we can write that down here. That is the same as the matrix of t1 plus B is the matrix of t2. Okay. Okay, so arithmetic is easy. We want t1 plus t2. We just add the outputs for t1 and for t2. And similarly for adding or subtracting matrices or multiplying by a scalar. Now we're going to do something very different. We are going to compose linear transformations. Now you do that in calculus, where you have seen the symbol f compose g of x. What does it mean? You plug in x into g, you find g of x, and you plug that into your function x. So sometimes we call them the inner function g and the outer function f. How are we going to do this for linear transformations? Well, we are going to input one of the transformations into the other. So let's go down to the bottom here. We will define t2 compose t1. Okay, so it's like f compose g. So what are we going to do? We will take t1 of v, we will input that into t2. Okay, so how is this going to work? Whatever output we get from t1 will be the output, the input rather, for t2. So that means that if t1 goes from Rn to Rk, if the output is in Rk, then t2 had better get its input from Rk, and its output can be any space that it wants. So from this setup, notice we have three spaces. We have Rn, the domain for t1. Rk is the codomain for t1, but is also the domain for t2. Rm is the codomain for t2. So the composition that we will create is t2 compose t1. Its domain will be in Rm. Okay, so the x in the composition will be a vector from the domain of t1, which is Rm. Its output eventually will be in Rm. Where did Rk go? It just disappeared. Okay, so how do we describe what's going on here? Let's put some symbols there. So we have v, our input vector from Rn. t1 of v, the output is u from Rk. U will be the input to t2, so t2 of u will be w from Rm. So now we can put it all together. t2 compose t1 of v is t2 evaluated at t1 of v. t1 of v is u, So this is the same as T2 of U, which is our output, our final output, W from Rm. So here's a diagram that describes what's going on here. Okay, so we have V, and we compute T1 of V. We're now in Rk. All right, so V is from Rn. It now transforms under T1 into a vector in Rk. Now what happens? We input U into T2. There's T2 of U, and we get the final vector W. So that transformation that starts with V skips over U and goes directly to W. That is the composition T2 composed T1. So please note that again, for this to make sense, the domain of T2, which is Rk, has to be the same as the codomain for T1, because whatever is output by T1 has to be input into T2. And we call that a compatibility requirement. Okay, so what is not obvious in this definition is that this composition is also a linear transformation, meaning it has to be both additive and homogeneous. So, as usual, let's prove the additivity property, and homogeneity will be a homework. So, we want to show that if you input V1 plus V2 into the composition, you should get exactly the same thing as if you input V1 and V2 individually into the composition and add the answers together. Okay, so how are we going to do this? Start with the definition. It says that we input V1 and V2 into T1, and then we input the whole thing into T2. So we have T2, the outer function, and then we have T1, the inner function, and we input V1 plus V2 into T1. Whatever answer we get there will be input into T2, which will give us the final output. Okay, but we know that T1 is additive, so therefore we can express what we see inside here as T1 of V1 plus T1 of V2. So let me make a copy here. T1 of V1 plus T1 of V2. So there it is. T1 of V1 plus V2, because T1 is additive, has to be the same as T1 of V1 plus T1 of V2. Okay, next step. This is input into T2, but T2 is also additive. So we can rewrite that expression also as a sum of two terms. So input this term into T2, so that has to go, and input this term into T2, so that has to go. Okay, so big picture, you have two vectors added together, input each vector individually into T2, we should get exactly the same thing. But wait a minute, T2 evaluated at P1 of V1. That's exactly the definition of the composition. So the first term is just T2 composed with T1, and we evaluate it at V1. And who is the other one? Of course, it is just T2 composed with T1, which we evaluate at V2. Alright, so there it is. That's the additivity property. T2 composed T1 evaluated at V1 plus V2 is exactly the same as if you would evaluate T2 composed with T1 only at V1 and added T2 composed T1 only at V2. Alright, so here's an example. Let's say that T1 is going from R3 to R2, and then T2 is going from R2 to R4. Okay, so who is T1? The input is x, y, z from R3. The output must be in R2. So we have 5x plus 3y minus z in the first component, minus 2x plus 7z in the second component. If that looks familiar, that was the same T1 in our previous example. But we have a very different T2. Okay, so this time T2 is going from R2 to R4. So to avoid confusion, let us write the input vector not as xy, but as uv. Okay, we're going to use different letters because we're going to plug in what we get from T1 into T2. That's how you do a composition. So let's better use different symbols. Where will uv go to? I need a vector in R4. So the first component, aq minus v. Second component, 3u by itself, no v. Third component, u plus 6v. Fourth component, negative u plus 9v. So that's 4 components. That's in R4. So let's check. Is the composition T2 compose T1 really defined? Are T2 and T1 compatible in that order? Because we're going to check. Maybe it should be T1 compose T2. I have these question marks all over the place. Let's make sure. So T1 is going from R3 to R2. T2 takes over and goes from R2 to R4. So yes, that composition, of course, is defined. And it starts at R3, the input for T1, and it finishes at R4, the output for T2. So that is T2 composed T1. Could we turn it around? Maybe, maybe not. What if you had T1 on the outside, T2 on the inside? So this time you start at T2, you go from R2 to R4, but wait a minute. Can we input that into T1? No, T1 needs an input from R3. So this composition is not defined. Now, in calculus and pre-calculus, you sometimes compose a function with itself. Okay, so you can plug in x squared into x squared, and you will get x squared squared or x to the fourth. Okay, that is very possible. Can we compose T1 with itself? T1 is going from R3 to R2. Oh, but wait a minute. The input for the outer function, which is also T1, has to be from R3, not R2. So, nope, this composition is not defined either. And of course, T2 compose T2 is not defined either. R2 to R4, you gotta start at R2, so no. Okay, so now that we know that it is possible, let's actually do it. How will we compute T2 compose T1 evaluated at XYZ? So, again, the definition says you take T2 as your outer function, and then you plug in XYZ into the inner function T1. Okay, so what's next? Well, we know what T1 of is, so T1 of XYZ is this vector over here. So that is what we input into T2. Okay, so this vector is what we will input into this formula, right? So in other words, we will think of the first component, this 5x plus 3y minus z. That will be our u in the formula for T2. And of course, the second component is our formula for v. Okay, so what do we get? Okay, so we will get, resuming our computations, this will be, okay, so let me put an empty vector. because we are going to compute 4 things. So I need 1, 2, 3, and 4. Okay, so what's the first thing? We want 8u minus v. So we want 8 times u is over here, minus v. Minus, who is v? Over here. Okay, and then, I better scoot up here. Now we need 3u by itself. Okay, so the second component is very short. We want 3 of u. 3 of u is over here. Okay, so notice we're just doing a substitution basically. Next, we need u plus 6v. Okay, so we don't really need parentheses for u, but I'm going to put it in. Okay, just to give us a visual cue that that portion of the term is from the u. Okay, and then we want plus 6v. So plus 6 of this. Okay, I hope we have enough space. Yeah, I think we're good. Finally, in the fourth component, we are going to get negative u, so we definitely need parentheses. I don't know about you, but the minus signs always give me trouble. There's our minus u, plus 9v. Okay, so 9v is over. Yeah, we got enough space. Okay, there you go. Beautiful vector. Okay, but of course, we want to simplify. Okay, so what have we got? Yeah, let's just copy that thing and let's expand those scalar products. So we have 40x, 8 times 3, 24y, and then minus 8z. Careful with those minus signs. Minus minus, we will get plus 2x minus 7z. So all of that is in the first component. Next, 3 times 5, 15x. 3 times 3, 9y. 3 times negative 1, minus 3. Next, so as I said, we did not really need those parentheses, so we'll just remove them. 6 times negative 2, so minus 12x. 6 times 7 is 42. 42z. Okay. This negative, be very careful, minus 5x minus 3y plus z. Okay, last parenthesis, 9 times negative 2 minus 18x, and 9 times 7 is 63. Okay, so getting close. Now we simplify each component. So what have we got here? 40 and 2x, we got 42x. Erase that. And then y by itself, minus 8 minus 7, minus 15. Okay. Next, oh, okay, it's all by itself. Yay. 5x minus 12x. So that is minus 7x. Okay, erase this. 3y by itself, yes. And then minus z plus 42z. That is 41z. Last term, minus 5x minus 18 minus 23x. Goodbye. Minus 3y by itself, z plus 63z, that is 64z. Okay, so that is the composition, T to compose T1 of x, y, z. So let's put that aside. Final. answer. Okay, let us summarize what we just did. We started out with P1 and P2, and we computed the composition. Okay, let's make matrices for these three transformations. P1, going from R3 to R2, so we need a 2 by 3 matrix. Keep remembering that they're flipped. So we need 2 by 3. So our matrix is 5, 3, minus 1 in row 1, negative 2, 0, there is no y, and 7 for z. Okay, that is the matrix for T1. For T2, from R2 to R4, so it's 4 by 2. 4 by 2. Okay, so we need 8, negative 1, 3u by itself, 3u, no v, and then 1 plus 6v, so 1 and 6, and then negative 1, u plus 9. Okay, so that is our matrix for T2. You know what, we're going to run out of space, so let me scoot them over into one line. Okay, now for T2 composed T1, we're going from R3 to R4, so we want a 4 by 3 matrix in there. 4 by 3. Okay, so we want 42, 24, minus 15. 42, 24, minus 15. Row 2, 15, 9, minus 3. Row 3, minus 7, 3, 41. Row 4, negative 23, minus 3, 64. Okay, so those are the three matrices that we get from this example. When we were just adding or subtracting or multiplying a linear transformation by a scalar, it was easy to see, well, where did this third matrix come from? Oh, we just add the pairs together. Well, you just multiply every entry by negative 4, okay? Here, where did all of these numbers come from? Well, they did come from these numbers, right? Because this was our u, 5x plus 3y minus z. That got multiplied by 8. And then we subtracted this because that was our v. Okay? So these numbers did come from these numbers. Okay? But is there a clearer, more systematic way to get this matrix from these two matrices? And of course, there is. Okay, and of course, that process is the general matrix product. We are going to multiply two matrices together, but before we can do that, we have to make sure that they are compatible. How do we know they're compatible? If A is an M by K matrix, then B will be a K by N matrix. Okay, so notice that the number of columns in A has to be the same as the number of rows of B. Okay, that's how we know that they are compatible. The number of columns of A must equal the number of rows. If they're compatible, then we can construct the matrix product AB. How big will it be? It will be M rows by N columns. So where did the K go? Oh, it disappeared, kind of like before. Okay, how do you find this matrix product? Well, hiding in column I of AB is the matrix A multiplied by column I of B. So here's an easy way to remember this. Partition B into its columns. So we have B1, B2 to Bn. Okay. Now each of these columns has k rows in it. Okay. A has k columns. So we can write the matrix product A times B1 and also A times B2 and so on. Okay. So those are the columns of A times B. Okay. So we said that this matrix that we got for the composition can be obtained from these two matrices by multiplying them together. Okay, there's only one small problem. They're not called A and B. Okay, so we have to decide who is the A, who is the B. Maybe it's this one. Okay, how do we do that? The number of columns of A must be equal to the number of rows of B. Okay, so are you the A? If this were A, we have 3 columns here, but 4 rows over here. Whoops, nope. So let's try this for the A. Okay, so the number of columns of A is 2, and the number of rows of B is also 2. So that is the correct assignment. Okay, this is our A, this is our B. Okay, so we will form the product A times B. Okay, so let's copy A down here, and let's copy B over here. Okay, so we know how to do the individual steps. We know how to multiply a matrix by one column. Okay, so the formula said, take matrix A on the left and multiply by the first column. Just the first column. So we know this. We've already done this before. You take 5 times the first column, negative 2 times the second column. You add them together. So click. That's the answer. Ooh, is that column 1 of the answer? Yes, of course it is. So let's try the other columns. Okay, I think we can fit them here. So you take A and you multiply by column 2. So you take 3 times column 1, no column 2 contribution. So you just triple column 1. Yes, of course, exactly the same. And last column, you take A and then you multiply by column 3. So negative 1 times the first column and add 7 of the second column. And thank goodness we get the correct answer for column 3. All right, so at least for this example, we showed that the matrix of the composition P2 compose P1 is exactly the same as the matrix product in the order B times A. So B was the matrix of P2, A was the matrix of P1. Okay, so it has to be in that order. P2 is first, followed by P1. And that's good because that's also the same order as the composition. P2 is first, P1 is second. So in the next section, we will prove that, of course, this is true in general. Now, to end this video, let's just take a look at another way to look at a matrix product. And we saw this in section 2.4, or maybe it was 2.5, where we looked at the matrix product with just one column as dot products. Okay, so if you had only one column, you will take row 1 of the matrix on the left and dot it with that column. So that's what we have over here. You have row 1 dot with B1. That's the first entry. Okay, the next entry in that column is row 2 dotted also with B1. So that's over here. Okay, so the first column in the matrix product are the rows of A dotted with column 1 of A. Okay, so this is a way to see how column 1 is formed as dot products using the rows of A with the same first column of B. And of course, the same idea for the second column of B. So it's the same row 1, row 2 to Rm as we see in column 1, but you dot each of those rows with the second column of B. Okay, so that is summed up in this theorem. So if you have an m by k matrix, A, and B is a k by n matrix, then the matrix product is m by n. And who do you find in row I, column j of the product A times B? You find row I of A dotted with column j of B. Okay, so that's it. That is our video for today. So thank you so much for watching. Again, you will find me on Facebook, and you will find the 4th edition on Facebook and at kendallhunt.com. So until our next video, I hope you enjoy the rest of the day.